Okay, so welcome to the second week of the course Linear Dynamical System on stability. So in this week, so this is the overall outline of the week 2, where we'll start with the introduction and origin of the stability analysis. Then we will see a brief review of norms and definite matrices. These tools would be useful for the rest of the topics in this module. Then we'll see the different definitions of the stability. We define and also determine the stability test in the sense of Lyapunov. We will also see the eigenvalue condition with respect to the Lyapunov stability. And finally, we will see the bounded input and bounded output stability and its connection with the Lyapunov stability. So here in this picture, you see the governor, the fly ball governor. So on the left hand side, that is in the figure A, this is the original design of the fly ball governor. So basically the governors are the devices which are used to control the motion of a machine. So here the machine is basically the engine. Then later on, the improved design of the governor you are seeing in the figure B. So the role here is to basically governor is the controller, where we want to control the speed of the engine. Now here, why, first of all, why do we call it the fly ball governor? Here you see the two balls. So whenever, and this shaft, basically this shaft is connected to the engine. So whenever the engine is rotating at some speed, these two balls either will fly apart or they will come closer depending on the motion of the engine. So here with the extended shaft, this is connected to the supply of the fuel. Here you see the opening of the fuel. Either the fuel is being supplied to the engine or the fuel is not being supplied to the engine. So let's see the motion of the governor. Let's say there is some desired speed which we have fixed for the motion of the engine. If the engine is rotating at a higher speed than the desired speed, so these two balls will fly apart, and because of the motion of these fly balls, this shaft will be brought down. Once it comes down, it goes up, meaning to say it will close the supply to the engine, supply of the fuel to the engine. And once the supply is stopped, the engine will rotate at a lower speed. So basically it is to control the speed of the engine. So this is in fact the first significant feedback control systems in the modern Europe. So at the height of the Industrial Revolution around 1868, many such governors were installed. In fact, there were many improvement in the design of the governors were established. But all those governor systems were highly plagued by the inaccuracy and the instability of their motion. So there was a very famous paper by Maxwell in 1868. So this paper is cited here. You could also see this paper is freely available on the internet if you would like to go a bit deep into what this paper talks about. So this paper brings many important things theoretically and also from the practical point of view. First of all, it introduces the concept of the stability. Second, this paper describes the simple mathematical models of the engine and the governors. It also highlights the importance of the integral actions, which you have possibly studied in your UG control course when you studied the specific part of proportional integrator and the derivative controller. Fourth is the linearization. Fifth and sixth, which are quite important, that stability is basically an algebraic problem. And the second last is, in this paper, some criteria for the first, second and third order systems were also given, that under what condition the system would be stable or the system would be unstable. So basically this paper posed the stability problem in competition, that how one can define the stability, and for the higher order systems or for the complex systems, the stability can be assessed. So there's a snapshot of this paper which I have uploaded here. So this is so here the important thing is In this, basically it is a continuation of some couple of equations starting from 1 to 10. So here he defined the motion of the machine itself by this complete differential equations, and then he computed the solution of the differential equation which we had seen in the week 1 of this course, and then he computed the roots of certain equation which is basically a polynomial of degree 3. So the important thing here, he computed the solution of such kind which we have studied, that basically the exponential solutions of the linear systems. And after computing the roots, he basically gave the conditions of the stability of the motions. So initially for the first, second and third order systems, he was able to write the conditions in terms of the eigenvalues or the roots of the characteristic polynomial. We will see a couple of things you have already seen in your UG course, and a much more detailed analysis in the sense of Lyapunov we'll try to discover in this module. So this is how he defines the stability concept, that the motion of a machine with its governor consists in general of uniform motion combined with the disturbance that may be expressed as the sum of several component motions. These components may be of 4 different kinds. Either it would be continually increasing, diminishing, or be an oscillation of continually increasing amplitude, and the oscillation of continually decreasing amplitude. Basically the idea is to see how the motion is being governed by this particular solution. So from your UG control course, you already know that the second and the fourth kinds are admissible in a good governor, because the response is is diminishing to 0 and are mathematically equivalent to the condition that all the possible roots, and here the possible roots are the real roots, and all the possible parts of the impossible roots. If the root is impossible, meaning to say if the root is complex, then the real part of that complex root of a characteristic equation shall be negative. We will see all of the connection of this negative and the positive eigenvalues or the roots of the characteristic polynomial with the in the sense of Lyapunov as well. So proceeding further with knowing the origin of the stability, here we will introduce a brief on the matrix norms and the vector norms, and also the positive and negative definite matrices. So a matrix norm is a norm on the vector space K of dimension m cross n, right? So first of all, you should be able to understand that why do we need a norm of a matrix or a vector for comparison purposes. Say for example, if you have some scalars value, let's say 2 and 4, if some scalar values are given to us, we know that the number 4 is greater than number 2 or vice versa, right? But if let's say a vector is given to you in the sense of 1 2 or 3 1, so these vectors could be a representations of many things. Let's say if you talk about the size of the human body, so the first element could be the width and the second element could be the height. So let's say here are two humans, H1 and H2, whose width and height is given in this format. So if we want to know the size of the human for the comparison purposes, how can we make this comparison? Because here we have two numbers. So the idea of the norm is to obtain a scalar value either for a vector or a matrix, so that you can compare two or more of the matrices or the vectors. So thus the matrix norms is a function which is defined by this, such that an m cross n dimensional space can be mapped into a scalar value that must satisfy the following properties: for all scalars alpha belonging to the field K, and for all matrices AB belonging to the dimension of m cross n, if that matrix is satisfying the property of homogeneity, meaning to say that the norm of the multiplication of the scalar alpha and the matrix is equal to the absolute value of that alpha and the norm of the matrix. Second is the triangular inequality, that the norm of the summation of two matrices is either less than or equal to the summation of their individual norms. positive value, that the norm is always positive or 0, and it would be 0 if and only if the matrix itself is a 0 matrix of the same dimension, right, which we call the definite. So several matrix norms are available for an m cross n matrix A, which are defined by this aij elements. So aij elements is I is defines the number of rows and j is the column of the matrix. So the first norm we define is the one norm. One norm is defined by, let's say a matrix is given to you A. So this basically means that I will sum up all the elements along the columns, and then I will compute the maximum of that single row. Say for example, if I let's say if I have two matrices 2 1 1 3, let's call it A1, and another matrix is 3 5. If I want to compute the one norm of this matrix A1, so it would be given by the maximum of, I will sum all the elements along the column. So the sum is 2 plus 1 is 3 and 3 plus 1 is 4, and the value is 4, right. Now similarly, if I want to compute the norm of this matrix A2, it would be given by the maximum of 5 plus 1 6 and 3 plus 1 4, so the number is 6. So here I know that the size of the matrix A2 is greater than the size of the matrix of A1. Right? Now if we have a column vector, then the one norm of the column vector is basically given by the summation of all the elements of that vector. The second norm is the infinity norm. Infinity norm is basically exactly the opposite of how we have computed the one norm. So in the infinity norm, we sum the elements along the rows and then we take the maximum out of it. Right? Say for again considering the example A1, 1 2 2 3. So the infinity norm of this matrix A1 is basically given by the maximum of summing along the rows. So here 1 plus 2 would become 3 and 2 plus 3 become 5. So the value would be given by 5. Okay. Now if we have a column vector, then the infinity norm of that column vector is basically the maximum element of that vector, which is given by this one, because here we don't have the second column to sum up the elements. Another norm is the 2 norm. So 2 norm is basically computed by the computing the largest singular value of the matrix A. Since we have not studied about this how to compute the singular values, you can also compute the 2 norm by computing the largest eigenvalue of the matrix, which is given by the multiplication of the transpose of that matrix by itself, and then taking the under root will give you the 2 norm. Now for a column vector, it is given by the square root of the summation of squared elements of that vector, right? Another norm, we have the Frobenius norm. So the Frobenius norm you can compute by this formula, where again sigma I denotes the singular values of the matrix A. If you do not want to compute the singular values, you can also use this formula to compute the Frobenius norm. So for column vectors, the Frobenius norm coincides with the 2 norm, meaning to say if you compute the Frobenius norm of the vector and the 2 norm of the vector, the values would certainly be equal. But in general, this is not true for the matrix. Okay. So keep this thing in mind. So there are a couple of norms which possibly we would be requiring to do our analysis later in this module. So the most important thing here is that all matrix norms are equivalent. You can use any matrix norm to compare two or more matrices. Say for example, let's talk about the vectors. Let's say we have one vector 1 2, another vector 2 3, and another vector, let's say 3 1. Okay, now if I want to compare that which vector is of the larger size than the other of the vectors. So if I compute the one norm would be given by the summation of all the elements, basically 3, and this one will yield 5 and this one will yield 4. So if I compute the infinity norm, it would be the maximum element 2, 3 and 3. Okay. If I compute the the 2 norm is given by under root 5 for this one, under root 13, 3 square 9 plus 2 square 4 under root 13, and for this one it would be under root 10. So if you compare all the values of the norms, you would see that the second vector is having the largest size, although when you are computing the infinity norm of that vector, its value is equal to the third vector, right? But it cannot go lower than the third vector, right? So when we say all matrices norms are equivalent, we actually mean to say, let's say I compute any norm, let's say called the P norm of the matrix A1 and the P norm of the matrix A2. Now if for any norm this relationship is satisfied, then for any of the P norm, P1 to infinity and the Frobenius norm, this relationship will always hold. Okay, although the value might change, as we have seen in this example here, that for the second vector, the 1 norm, infinity norm and the 2 norm are having different values with respect to the first and the third vector, right? So if you also want to compute the relationship between the different matrix norm, this relationship you can use to compute those values, where m and n basically defines the dimension of the matrix. So the 4 matrix norm what we had discussed above are sum multiplicative, in the sense that the norm of the multiplication of two matrices is basically less than equal to the multiplication of their individual norm, and I wrote this P because P belongs to 1 to infinity and all including the Frobenius norm. So for any sum multiplicative norm, we have this relationship. If I replace B by the vector X, then I would compute the P norm of the matrix using this relationship as well, which would be always greater than equal to the maximum value of the ratio of the P matrix norm of the AX and the P vector norm of the X, where X is not equal to 0.